Good morning. Welcome to the last webinar in the series of webinars brought to you by the INFRACHIP project, all on the topic of sensing. As with the previous webinars, I want to remind you that most of the things that you will see today, they are let's say, created using the expertise and the technologies and the equipment that you can request access to through InfraChip. So if you see something that you like or that you potentially think might be interesting for your research, then definitely get in touch with the InfraChip central office, and we will put you in touch with the technical teams that can discuss with you if some of these technologies or platforms could be implemented for the purposes of your projects. And today, our speaker is Miguel Franco, and with the PhD in materials engineering, he focused in the field of printed electronics. For example, he worked on flexible and wearable electronics, fabricating a large array of sensors, thermal, piezoresistive, and humidity sensors. And also since 2017, he has been working on environmentally friendly ink formulations tuned for specific printing techniques. And so that's obviously very well aligned with the topic of the webinar today. And so the idea behind the webinar today is that it is becoming more and more interesting and practical to create some electronic devices using printing methods, because it is a relatively low cost and high volume method to make inexpensive devices, and at the same time also to make devices with a wide range of functionalities, which include sensors, actuators, and the supporting electronics. And of course, the printing techniques that you will see some examples of today, they can be screen printing or inkjet printing, and they enable production of these different types of devices, including on flexible substrates. And so again, obviously, this is very applicable to, for example, wearable technologies. At the same time, one of the challenges is that the ink formulations often involve some materials that are not so environmentally friendly. So in this particular presentation, the focus will be on looking at the ink formulations, both the, let's say, particles in the ink and also some of the solvents that are more environmentally friendly and yet allow the final printed devices to retain high performance and all the functionalities that can be achieved using these methods. And so with this, I will hand over to our speaker. And in this webinar, you can see that there is a question and answer facility. So during the presentation, you can already start writing the questions, and then once the presentation is finished, we will have a question and answer period. So again, you can either submit your questions during the presentation or during that question and answer period in the end. And with this, we can go ahead and start the presentation.
Thank you, Dimitri, for giving the floor and introducing myself. I'd like to thank to the audience present in this webinar. During the next 40 minutes, I want to give the potential of printing electronics in sensor fabrication. Especially, I will highlight the versatility of graphene as a sensing layer. This presentation is entitled of Environmental Friendly Graphene-based Inks for Sensing Electronics. The Cinemat and UNINOVA buildings are situated in Nova School of Science and Technology. It is located in Caparica, 5 kilometers south of Lisbon. The campus is 5 kilometers away from the famous Paprika Beaches. This center is a center of excellence, generated more than 1,600 papers, 70% in high-ranking journals with an H index of 111. Over the years, the Adrian researchers have achieved excellent scientific results, recognized with award of 11 ERC grants, as well as the number of international projects and patents, along with scientific papers published in high-impact journals, making the Adrian Center the leading research institute in Portugal in the area of material science and nanotechnologies, supported by a common and relevant activity related to materials and device characterization, device physics, modeling, and simulation. During the last years, I3N has consolidated its strategic research activity in order to meet the innovation challenges associated with nanotechnologies, nanomaterials, and nanosciences in accordance with the policies established by the Horizon 2020, with the purpose of improving the level of material science and technology understanding and their use as a key enabler of multi-sector applications. Currently, the research thematic lines are divided in 4 teams: the sustainable micro and nano fabrication, the green and clean energy systems, nanomaterials and engineering and functional interfaces, and biomedical device and systems. The cinema at I3N/UNINOVA state-of-the-art facilities that allows microelectronic characterization and its fabrication and its characterization. We have a clean room with a quasi 1,000 room, a yellow zone, equipped with all tools necessary to perform photolithography process in microelectronics. Additionally, there is a production room with a wide range of physical and chemical vapor deposition tools to fabricate a variety of thin film materials, from metals, transparent conductors, to semiconductors and isolators. Also, there is a atomic layer deposition system. Then we have state-of-the-art characterization labs for both electrical characterization with several probe stations with semiconductor parameter analyzers, and material characterization, in this case STM, SEM, or XPS. During my doctoral thesis, which part of the results I'm going to present, I focus on the development of conductive inks and memory-stiff active material for critical electronic applications, namely memory stores and sensors. In this case, for this presentation, I will highlight the sensors. It was supervised by Professor Sanancho Aceros Mendes from University, whose focus is on building new sustainable materials and devices focused on sensors and actuators, and co-supervised by Dr. Azal Kiazade from Senimat Itrian, whose focus is on memory stores for energy-efficient new computing paradigms. So, why the focus on printing electronics? As you are aware, society evolution follows an exponential trend. It took thousands of years to evolve from an antique society into an industrial society. Only during the last century, society has evolved into an information society. Nevertheless, society is currently transitioning into a smart society where sensors will be connected into a worldwide network. To achieve the transition into a society 5.0, we need new materials, efficient microarchitectures, and low-cost mass production fabrication techniques. As you are aware, most of the electronic devices are based on silicon integrated circuits. Yet, for applications where high processing speed is not a key requirement for such sensors or display or some types of displays, printing electronics is a competing alternative which provides high throughput position on large areas, which allows the use of flexible substrates. This area is progressing quite a lot during the last years, especially on Asia, where TCL, a Chinese company, a display company, display on CES, a commercial fair, inkjets, a commercial inkjet 65-inch 8K flexible OLED panel. So, with the advent of Internet of Things, of IoT, it generates a high demand of sensor manufacturing. It creates a rising trend on integration of print electronics with wearable technologies. Therefore, as a first step, there is the concept of hybrid electronics, where sensors, displays, antennas are built using printing techniques, and silicon chips are integrated for signal processing tasks. Currently, the printing electronics market size is estimated at $14 billion, with estimated year-over-year growth of 17%. This industry will play an impactful role into the transition into a smart society during the next decades. This next, I will introduce or try to deep the printing techniques. Printing techniques tends to be additive manufacturing techniques. It can be divided into three main categories. Non-contact printing techniques, which tends to be droplet based, such as inkjet printing, aerosol, or electrodynamic inkjet. Then you have contact techniques, which tends to be rotary compatible. You have reverse offset printing, gravel printing, or screen printing. The first techniques widely used on printing electronics and currently the most used. And lately, there start to emerge extrusion-based printing techniques that allows precise deposition of pastes with minimal wastes. In the aerosol printing technique, here in this technique, the ink is aerosolized and carried by nitrogen gas and sprayed in substrates. The main advantage, for example, of this technique is that it allows the deposits compact shades, allowing conformable printing. Then we have inkjet printing is a non-contact printing method based on positive marking droplets into a substrate. The droplets, which tends to have a diameter between 10 to 50 micrometers, is manipulated under digital control. An inkjet system comprises a digital control printer that projects inks to droplets. Most of the printing systems use a drop-on-demand inkjet system, which we tend to use a piezoelectric printer. This technique can achieve a printing resolution or a maximum printing resolution of 15 micrometers and can be widely scalable to industry because it can enable multi-nozzle printers and multiple printers in parallel printing. Nonetheless, the main drawback of this technique is the strict ink hierarchy to achieve reliable jetting. Then there is hydrodynamic inkjet printing. It starts as an advancement of inkjet printing in terms of printing resolution. It can achieve a printing resolution up to 40 nanometers, and the working principle is identical to electrospinning, where it tends to draw ink rather than pushing it out, like on drop-on-demand inkjets. Since it relies on electric fields, the ink must contain electrical charges, and there are challenges when using multi-nozzles due to the crosstalk, which can limit the scalability to industry. Then I will introduce some contact printing techniques. We have gravure printing. Gravure printing, when the design elements are engraved into a printing cylinder surface with a partial fill ink fountain. The engraved printing cylinder revolves. The entire surface of the cylinder collects inks from the fountain, where excess is removed by electrode blades from the non-image areas, leaving the ink on engraved cells. The ink is then transferred directly from the cells to the substrates in the printing nib under pressure. This technique is widely used on the graphing industry. this that permits high throughput. However, the main limitation on this printing technique at lab scale is changing the design requires new cylinders, so it tends to be very costly. Then you have reverse offset printing that allows high quality thin film deposition by those of quiches. While likewise in gravure printing, changing house design also requires the new quiches can be quite expensive. Finally, I will introduce the most versatile, the most common printing technique and used on this representation, which is screen printing. It is one of the most popular deposition methods for printing electronics, which use screen masks to deposit materials onto a large area substrates. Because of this use, scalability, environmental friendliness, and high throughput, these techniques also have great promise for low-cost mass production of large area electronics and easily scalable to the industry. Here is a summary of the advantages and challenges of contact and non-contact printing techniques. Contact printing techniques allows high-speed printing and being row-to-row compatible. However, changing the changing the design requires the fabrication of new mask cylinders, it is a big drawback at research level and design optimization. Screen printing is a more affordable technique, but for thin film applications, it is limited by high surface roughness and to achieve thickness lower than 1 micrometer. However, for sensors or to deposit thick films, it is an excellent and reliable printing deposition technique. By the other hand, we have non-contact printing techniques, which permits the deposition of thin films with controlled thickness. And since it is a digital technique, it is easier to change the design by changing the input file. However, the hard coffee ring effect and stricter ink rheology and particle size that can be a constraint when formulating certain types of inks or to deposit certain materials. Here, I can show the printing equipment present on Cinema i3N. There is an automatic screen printing machine. There is two inkjet printing machines. One Pixro LP50 in side clean room and Andy Mattings inside clean room who achieve thin film deposition without any contamination or any dust that can destroy the device. Also, there is a flexographic machine, and right with arrive, we are testing and is try to use high resolution printing machines. In this case, this is a high resolution extruder from XTPL. We can achieve printing the resolution under 5 micrometers. This is an example of the XTPL printing on Cenimat. In this case, in this system, we only print so far silver inks, silver pastes, or gold pastes. So, since I explained the printing techniques, I need to explain another key component of the printing electronics. In this case, is the ink itself. One key part of key part of printing electronics is the design of the ink. In a very simplistic way, the ink is composed by the filler and additives which are dispersed or dissolved with a solvent. Usually, the solvent are the most hazardous constituent. Therefore, there is increasing concern to replace hazardous solvents like DMF or an NNP, which going to be banned by environmentally friendly solvents. This is a growing market, but it is still in the very small market is with under $1 billion market size. And hopefully during to achieve a sustainable transition, we hope soon we can change the information based on knowledge that and aromatic solvents, which tends to be toxic and unstable, into a power protic solvents. In this, to keep the sustainability, for the sensors, we use graphene. Why graphene? Because graphene is a carbon element, and carbon is abundant element in this planet and can be produced in a sustainable way. One, graphene is one form of carbon allotrope, a 2D material that can be grown by chemical vapor deposition, CVD, can be laser-induced graphene, and for printing electronics, it is foliated from graphite in a foam wall and generated as a reduced graphene oxide. The graphene itself shows high electrical and thermoconductivity and with excellent mechanical strength. Printed carbon allotropes can be found on printed circuits such as on diodes, capacitors, transistors, memory stores, and as a large variety of sensors and antennas. When designing the ink, it is needed to optimize the ink formulation. Particle size is a limiting factor of printing resolution. To achieve high resolution, especially to, to achieve high resolution, it requires full opening meshes and this this places stricter particle size in order to avoid clogging. In case for high resolution extruders using high resolution nozzles, small nozzles, in the place they use, for example, of nanoparticle-based spaces can be a challenge. To keep the ink stable and avoid agglomeration, or to improve adhesion, or even to tune surface tension, or even avoid foaming that can happen on screen printing, it is important to add stabilizers in the form of polymers or small molecules. Also, as an initial step for conductive inks, it is to find a percolation threshold that, in case for graphene, it tends to vary a lot in weight percentage when using different sorts of graphene, since its volume and density change a lot when changing different types of graphene. In this case, our graphene formulations use the same protocol. It was used mechanical mixing. This can be easily scaled into large volume. First, the binder was added and so rotation speed, and then graphene was added at maximum mixing speed. In this case, 2000 RPM because it was limited to the equipment itself. The inks were optimized for screen printing techniques, and first it was studied the fuel influence using PVP and Siren. Then it was studied the binary influence. In this case, three different types of binders were used. This we use a chemical resistance PVDF in the MPU, a elastomer SCBS in P-Simin, and PVP in water. It is to remind that all these solvents tends to be environmentally friendly alternatives, especially sirens. It is a biodegradable solvent, which is an alternative to DMF on NP, and this solvent has a great capacity to stabilize graphene that allows stable graphene dispersions with high concentrations. Why use screen printing for sensor fabrication? First, it is the most adopted printing technique in the industry, and it can achieve high rate of resolution up to 20 micrometers if using stainless steel meshes. In the first study, two different commercial graphenes were used, reduced graphene oxide and a nitrogen doped reduced graphene oxide. It was used polyvinyl polyhedron as binder and acylene as solvent. For comparison, the graphene concentration are kept as 25 grams per liters and the graphene binder ratio of 25 graphene-75 binder. To the low density of reduced graphene oxide, its viscosity is almost one order of magnitude higher than nitrogen-doped graphene. Moreover, to this higher specific surface area, it need of reduced graphene oxide, it needs more polymer to stabilize hensing, hensing having a worse adhesion than nitrogen-doped graphene. For those two reasons, it was selected nitrogen-doped graphene for the next study, which in this study, then it was studied influence on binder. It was used nitrogen-doped graphene oxide, the same as previous, and the concentration was increased to 75 grams per liter. The graphene binder ratio was changed in order to find an optimal one. To find the optimal fuel binder ratio, but it was used three criteria. First, criteria was a printing quality. For that, electrical pad was selected to evaluate the printing definition. It was found for the ratio of one graphene for two of binder, shown better definition when comparing the different polymers itself, PVP shown better printing uniformity. The second criteria was adhesion, and here we can discard these two formulations which have a lower amount of binder. By analyzing the microindentation data, the displacement largely increases when increasing the fuel binding relation from 1 to 2 to 2 to 3. When comparing to the different polymers, PVP shows the best adhesion with the lowest displacement and with highest youngest mode. The final criteria was to evaluate the sheet resistance of the films for, you can see for fewer binder ratio above 1 to 2, the sheet resistance stabilizes, meaning meaning that these formulations are well above precaution threshold. There is no significant change in sheet resistance between different binders, with sheet resistance between 80 and 100 ohm per square. I have to highlight that these results were using low temperature thermoannealing, which is under 120 degrees Celsius, which can be allowed to print on a wide array of flexible and temperature sensitive substrates. By exclusion, it selected the ratio of one graphene to two of binder. To test its mechanical properties, all films were subjected to bending testings. All the formation withstand 100 cycles and bending of 5 millimeters ratios, and SCBS shows piezo resistivity with a gauge factor of 4. Also, thermoforming was tested as a proof of idea for conformable electronics. PETG was used as a substrate, and after conformation only PVP withstand without increase of wine resistance. By surprise, SCB as elastomer shown increase of resistance due to the presence of microcracks after conformation. Now I highlight some applications of the graphene on sensors. In this case, it was used as another commercial graphene, and I need to highlight since it has a different intrinsic properties. It needed to do another optimization of the ink ratio. I need to highlight that because since graphene has different types of graphene has very different intrinsic properties such as surface area and fall and density, it greatly changes its rheological properties of the inks. It was found the percolation threshold is around 3% in weight, and it can achieve a sheet resistance of 200 ohm per square when above percolation threshold. In this case, it was used a natural drive carbon methyl cellulose was used in a mixture of water and ethanol. Also, you can see the thickness tends to increase when increasing the graphene loading from 2 micrometers with a ratio of 10 graphene to 19 cmc to 19 micrometers with a ratio of 19 of graphene and 10 of CMC. Taking into account the per question data, it was using the, this formulation is assessing where since it is close to the per question threshold to aim higher sensitivity, why at a critical fuel concentration, rapid change in the direction of electrical properties is observed when interconnected conductive fuel networks are formed. The formulation with the highest graphene content was used as an electrode. The sensors can work as a as a temperature sensor, where two range of temperatures were tested, one between 30 and to 40 degrees Celsius to estimate human body temperature, and then between 40 and 100 degrees Celsius for automotive applications. Also, these sensors can work as a piezoresistive sensors with a gauge effect up to 4 high ferrous based composites. Also, the most conductive formulation, this same formulation, were employed as a sensing layer of a capacitive touchscreen device. In this case, with cooperation with this Plex, a touchscreen company, a screen printing 8-inch capacitive touchscreen device were fabricated. It was used the graphene, as I said before, it was used graphene as the sensing electrodes, and for the interconnections, silver was used. This is quite a large. This is the size of A4 sheet, and as you can see, it was the spacing between these slides is very low. It's under 200 micrometers without having any short circuits. That can show the capabilities of the screen printing techniques on its lateral resolution. In this capacitive sensor, the PET acted as a dielectric layer. The device is encapsulated with glass, followed by the connection of the flat flexible printed circuit. Finally, it is connected. The hardware, the PCB hardware that detects the multi-touch. Here, in this figure, it represents the touch test detection process and the response signal according to its activation. Within the presence of the finger, it triggers a local change of capacitance, where can be read by the circuit. The printing capacitive sensor has a signal to noise ratio around 10 for a matrix composed by 40 columns and 28 rows. Here is a demonstration of the touchscreen device in action. Also, it allows multi-touch capabilities. Finally, humidity sensors were also building in collaboration with Vice in Sweden and BC Material and with BC Materials in Bilbao. And this is work ready for submission. In this case, screen printed humidity sensor based on graphene was fabricated. Two structures were adopted. One as a resistive sensor with the with as a, with the reduced graphene oxide acting as a sensing wire sandwiched between two silver electrodes, or as a graphene field effect transistor acting as a sensor. The sensors can achieve change of resistance up to 4.25 ohms per change of resisting ohmity using in resistive as a resistive sensor or as 0.19% per percentage of change of resistance of humidity in current or in change of current in GFET mode while also showing good linearity. The major advantage of using conductive reduced graphene oxide-based sensor is their readability in resistive modes of transaction and fixed low impedance at low levels. This allows the possibility of incorporation these sensors in low power commercially available microcontrollers for sensing applications, thus eliminating the needs for complex impedance and capacitive measurement systems. Also, these sensors has a quick response time, up to 5 seconds, that can be used to detect nose breathing or even the touch finger. This device also has robust and can withstand cycles. As a final remarks, there is environmentally friendly formulation. By formulated, linked to these key properties of graphene that plays a key role of rheology, electrical conductivity and adhesion. For screen printing, graphene is promising sensing applications and electrodes, and for applications, piezo resistivity and temperature sensors are developed. It was developed at printing 8-inch capacitive touchscreen devices or as humidity sensors. These types of fuels and solvents and infrastructures are present in Cinemats, and if you are interested, you can contact UNINOVA to use the extensive equipments and insider knowledge. So thank you for your attention.
Thank you very much for this interesting presentation about the printing electronics, and also about the some of the details about the ink formulations and how to try to make them more sustainable. So now we're opening the question and answer period. So you can find the question and answer tab, well, somewhere on your screen. So I think it's typically at the bottom of the screen. So you can type your questions there. And we have the first question. How does the viscosity play a role in the film uniformity in screen printing? And how best to design inks for different filler materials for screen printing?
I will. I can show this slide. So in terms of in terms of real viscosity, the screen printing technique is quite versatile on viscosity itself. The most important requirement for in terms of viscosity is the ink should have a non-Newtonian behavior, like that. So it tends to be quite viscous when no force is applied. When the squeegee is applied, force is applied, tends to be fluid enough to pass through the meshes. So in this case, about the ink design, it depends about the intrinsic property of the filler, and due to these intrinsic properties, we need to study and to design the amount of binder needed to stabilize and to have the desirable characteristics. For example, graphene, since it has a very low density and a very high specific surface area, it's very hard to make inks with a higher graphene content in terms of weight percentage. But for example, if you were using oxides or another kind of fillers, you can see these values quite higher. I don't know if I can answer the question.
Well, maybe another aspect. So, is there, for example, a difference in terms of ink formulation for the conductive inks versus the inks that are using like semiconductor or oxide materials?
In this case, for semiconductor is quite different because you want also to preserve its carrier characteristics and its mobility. So you need also to decrease the minimum amount of binder possible that because adding a binder can also degrade the semiconductor performance. So there is also, this is another balance for those type of inks.
All right. Thank you for this detailed answer. So I hope that this was that this was what the question asker expected. Are there any other questions from the audience? Okay, so go ahead and type them up. So while we're waiting, I think I have one question that I'm kind of curious about. So you mentioned using the humidity sensor to detect a touch. So
Yeah, that was.
is that based on the, let's say, humidity or the small amount of water on the tip of the finger, or what is it? How was the detection working?
In this case, by the smallest change of resistance, it tends to be the presence of water itself,
Right. So
not
it's
by the pressure,
Mhm.
not the pressure itself.
Right. So this basically relies on having a little bit of sweat or some other
Yes, yes,
water on the finger. So I guess if it's like really cold or really dry, then it may not work as well.
yes, yes, exactly.
Okay. Okay. All right. So in the meantime, we have additional questions here. There are many ways to prepare graphene. Which methods to prepare graphene work best for printing?
In this case, to avoid another set of variables, I use commercially available graphene. But in this case, we're from exfoliated graphene. Right now at Sanimat, there is try to make high quality graphene by exfoliation from graphene using sustainable solvents for using styrene or using even uh, using another using styrene and using sonication or tip sonication technique. In this case, for printing electronics, we tends to use reduced graphene oxides. But there is another interesting approach, for example, for sensor fabrication, which is interesting on available on Cenimat, which has a lot of high expertise, is on laser-induced graphene, and you can use laser beam to generate graphene. There is another interesting approach. We did some challenges, but it's another interesting approach. Also available in Cenimat.
All right. And another question is every method contains some other materials in the ink. Do these materials affect the printing process, and how can you prevent? So I guess in this case, maybe we're talking about additives or contaminants.
The well, when I, yeah, so for screen printing techniques, it tends to add additives, tends to be adding additives for to increase the viscosity of the ink itself and to give adhesion. However, there is a trade-off. So if you add put a lot of binders, you can degrade the electrical conductivity. So because you are forming composites in this case of on the screen printing technique. But small amounts of stabilizers is very important because if you have a mismatch on surface tension, you can also have a very poor printing resolution. And then if you want to achieve high resolution, you need to make the best thing possible. So you need to take account of these factors: surface tensions, foaming or defoaming. So the printing, the formation itself will use a mixture of several stabilizers. This is more relevant on inkjet printing.
And have you experienced some cases when you had unintentional contamination of the ink of something that you were not aware of in the material?
Not for screen printing, not necessarily. I during my PhD also managed to develop inks for inkjet printing, which is much more challenging. That case, contaminants or particle size is very troublesome for inkjet printing because it can easily clogs the nozzles and can be very tricky. In this, for inkjet printing is more sensitive. Contaminants is more sensitive rather than screen printing because it's more the ink tends to have a lot of more solid contents, and if you add a small contaminant, the percentage is much lower than compare the same amount of contaminant on inkjet ink.
All right. So another question is about these formulations being environmentally friendly. So perhaps you can summarize what aspects of the formulations that you told us about make them more environmentally friendly than the current standards.
Well, course, well, one of the most used we used solvent used to disperse graphene tends to be NMP or DMF. Those solvents are quite harmful, and I think European Union is going to ban these solvents soon, before 2030. It's in progress. I don't know if it's going to happen or just happen just for that. There are some green alternatives. In this case, Irene. It was starts to be published in 2 or 3, 5 or 6 years ago. This solvent has a much lower toxicity than rather than an NPR DMF. Also, this solvent is biodegradable, unlike DMF and NMP. So, and it allows a great dispersion of graphene. You can achieve very stable dispersion of graphene or carbon nanotubes with a high concentration. For the other inks, for example, PVDF tends to be dissolved on DMF, so DMPU can be seen as an environmentally friendly alternative. The CBS, it will use P-Cymene. P-Cymene is a greener, more sustainable alternative than toluene. Toluene is quite toxic. And PVP use water soluble, so water is quite, it's the most green solvents available.
All right. Thank you. All right. So the next question, I have to confess, I'm not familiar with this abbreviation. Hopefully, you are. So for printed electronics, devices, what is the role of LIG? Can we consider it more reliable than other methods?
LIG, I think he meant laser-induced graphene,
Okay.
probably.
Probably.
If
Okay.
okay, if laser-induced graphene, yeah,
Yes,
can
that's
be.
correct.
Laser-induced graphene is very interesting because you can achieve very conductive graphene because there is no binder. The challenge of the laser-induced graphene is the adhesion itself. You need to try to stick it. Probably this is the main challenge of laser-induced graphene is to try to stabilize it, to stick it. Because if you just induce graphene, it tends to easily fail out, easy to escape. So it needs to be well passivated.
Okay. All right. So the next question is, since you selected different graphene oxide ratios for each binder, how did you determine that the mechanically exfoliated graphene oxides exhibits consistent properties across all the different binders that you tried?
Because I use a commercial graphene, so the property in this case the intrinsic properties should be the same. In this case, I just changed the figures, the ratios, just for information. So it was you expect using a higher binder amount like this one, you should get a higher adhesion, but in the trade-off of lower conductivity or for this one. But if you are above percussion threshold, there is no significant changes in cheat resistance, but however, the adhesion properties of the films it tends to increase to worsen a lot.
All right. Thank you. Let's see. Let's give it another few seconds for people to type if there are any additional questions. All right. Okay. So it looks like we're done with the questions. Again, I thank everyone for attending this webinar, which is the last in the series about different platforms and technologies to prepare sensors. Brought to you by the INFRACHIP project. I hope that some of you had a chance to attend other webinars in this series. And of course, as we saw some interest in these type of activities, the project will run some additional series of webinars in the future. So if you follow the LinkedIn profile of the project, you will get notifications about the additional webinars, and of course, also if you subscribe for our letters and so on. Because obviously in INFRACHIP we have a variety of technology platforms that we're supporting. So again, I thank you for attending this webinar. And as we mentioned before, so if something that you saw today looks interesting or potentially interesting for your research, then definitely get in touch with the INFRACHIP project, and we will try to connect you with the people with the best expertise in these technologies. So, for example, in these printed electronics that we heard about today. And with this, I thank again both the presenter and the audience, and I hope that you will join the future webinar series offered to you by the INFRACHIP project. Thank you. Bye-bye.